that every homomorphic image of an abelian group is abelian. Let G be an abelian group and G dash be a group. Now we have to show that every homomorphic image of an abelian group is abelian. So first we have to define a mapping from a group G onto a group G dash. So F maps from G tends to G dash is a homomorphism onto. Therefore f of G is equal to G dash. So now our claim is f of G is equal to G dash. So we know that f of G is equal to G dash, that is equal to f of A such that A belongs to G. Clearly f of G is a group. Let A dash comma B dash belongs to G, then there exists A comma B belongs to G such that A dash is equal to A f of A and B dash is equal to f of B. Now consider A dash B dash is equal to f of A dot f of B, that is equal to f of AB, f of AB. Since f is homomorphism, then we know that f of AB is equal to f of B. So G is abelian, A dot B is equal to B dot A, so f of AB becomes f of BA. So f of B again can be written as f of B dot f of A, since f is homomorphism. Therefore A dash B dash is equal to B dash A dash. Therefore f of G is abelian group. Every homomorphic image of an abelian group is abelian group. Next definition of kernel of a homomorphism. If f is a homomorphism of a group G into a group G dash, the set of all those elements of a group G which are mapped by f onto the identity E dash of G dash is called kernel of the homomorphism F. Kernel F is equal to x belongs to G such that f of x is equal to E dash, where E dash is identity element in G dash. If f is a homomorphism of a group G into a group G dash, then kernel F is a normal subgroup of a group G. So first we have to suppose that f is a homomorphism of a group G into a group G dash. Then we have to define a mapping f from G into G dash is a homomorphism. Here G comma G dash be two groups, then we have E is the identity element for G and E dash is the identity for G dash. Therefore E comma E dash be identity elements in G comma G dash respectively. Let kernel F is equal to K. Since E belongs to G implies E belongs to K. So K is a non-empty subset of a group G. So A comma B belongs to K and kernel F is equal to f of A is equal to E dash and f of B is equal to E dash. Now consider f of AB whole inverse is equal to f of A into f of B inverse, f of A into f of B whole inverse, since f is homomorphism. So E dash into E dash whole power minus 1 is equal to E dash. So A B inverse belongs to K. Therefore K is a subgroup of a group G. To show that K is a normal subgroup of G, so we have to know that K is a normal subgroup of G means x inverse belongs to K, then K is a normal subgroup of G. F of G K G inverse is equal to f of G into f of K1 into f of G inverse. So f of G into E dash into f of G whole inverse, that is equal to E dash. So f of G into K into G dash is equal to E dash. So G K G inverse belongs to K. So K is equal to kernel F is a normal subgroup of a group G. The next theorem, the necessary and sufficient condition for a homomorphism of a group G onto a group G dash with kernel K to be an isomorphism of group G into G dash is that kernel F is equal to singleton E. Here we have to take two groups G comma G dash. So G is an identity element and G dash has an identity element. So E comma E dash be two identity elements in G and G dash respectively. F maps from G into G dash and on to homomorphism. Therefore ker F is equal to x belongs to G such that f of x is equal to E dash identity in G dash. Suppose that f maps from G tends to G dash is an isomorphism. Therefore f is 1 1. Now we have to show that kernel F is equal to singleton E. So let x belongs to kernel F, f of x is equal to E dash. implies f of x is equal to f of e, implies x is equal to e. Therefore f is homomorphism and f is 1 1. Kernel f is equal to singleton e. Conversely, suppose that kernel f is equal to singleton e, we have to show that f is an isomorphism. Now it is enough to show that f is 1 1. A comma b belongs to G such that f of a is equal to f of b. F of a into f of b whole inverse is equal to e dash. F of a into f of b whole inverse is equal to f of b inverse. So again f is homomorphism. F of a into f of b inverse is equal to e dash. So f of a b inverse is equal to e dash. So a b inverse belongs to kernel f. Kernel f is equal to singleton e. So a b inverse is equal to e. So which implies a is equal to b. Therefore f of a is equal to f of b. Implies a is equal to b. Therefore f is 1 1. F maps from G tends to G dash is an isomorphism. Therefore every homomorphic image of n, the necessary condition for homomorphism of a group G into a group G dash is kernel f is equal to singleton e. Next, let G be a group and n be a subgroup of a group G and f be a mapping from G to G by n defined by f of x is equal to nx. For all x belongs to G, then prove that f is a homomorphism of a group G onto a G by n and kernel f is equal to n. Let G be a group and n be a normal subgroup of a group G and f be a mapping from G to G by n defined by f of x is equal to n nx for all x belongs to G. Then prove that f is a homomorphism of G onto G by n and kernel f is equal to n. G be a group and n be a normal subgroup of G. G by n is equal to nx such that x belongs to G is a quotient group. So now define a mapping f from G tends to G by n. F of x is equal to nx for all x belongs to G. Now we show that f is an onto homomorphism. Let x comma y belongs to G. F of xy is equal to nxy, nx dot ny, f of x dot f of y. So f of xy. Therefore f is homomorphism. Now to show that f is onto, let nx belongs to G by n implies x belongs to G. For every nx belongs to G by n, there exists x belongs to G such that f of x is equal to nx. Therefore f is onto. F is an onto homomorphism. Now we show that kernel f is equal to n. We know that kernel f is equal to k. X belongs to G such that f of x is equal to ne. Identity in G by n. Now we show that k is equal to n. So f of x1 is equal to ne, that is equal to n. F of k1 is equal to n k1. K1 belongs to capital N. So k1 belongs to capital K, k1 belongs to n. So k is contained in n belongs to capital N belongs to G. So f of n is equal to small n into capital N. Therefore small n belongs to k. Therefore n is contained in k. Kernel f is equal to small n is equal to k. So next a mapping f from G tends to G by n defined by a f of x is equal to nx is called canonical homomorphism or natural homomorphism. Fundamental theorem of homomorphism of groups. Prove that every homomorphic image of a group G into G dash is isomorphic to some quotient group. Or if phi is a homomorphism from a group G onto a group G dash, then prove that G by kernel phi is isomorphic with G dash. F maps from G tends to G dash is a homomorphism and onto with the kernel K, then G by K is isomorphic to G dash. Let G comma G dash be two groups given that F maps from G tends to G dash is an onto homomorphism with kernel K. Clearly K is a normal subgroup of G. So G by K is equal to Ka such that A belongs to G is a group. Phi is mapping from G by K tends to G dash defined by phi of Ka is equal to f of A. Now to prove that G by K is isomorphic to G dash. So first we have to show that our phi is well defined. Next we have to show that phi is 1 1 and next we have to show that phi is onto. then pi is homomorphism, that is pi of k dot kb is equal to pi of k dot kb. Therefore pi is homomorphism. Therefore pi maps from g by k tends to g dash is a homomorphism 1 1 on 2. Therefore pi maps from g by k tends to g dash is an isomorphism.